Okay, this is booklet 6 or week 6 out of 6, the last booklet, and it's a paper 1 booklet. It starts with a list of all our revision for paper 1. A couple of things that are actually in a calculator paper in booklet 1, Pythag and SOCAR they're on the list for both papers. We'll go into how they could be asked without a calculator, okay, but you know kind of what you're doing with them. Booklet 2 is all non-calculator. Nothing in booklet 3 that I think you need to revise for paper 1. Booklet 4 again is all non-calculator. The bold things are higher tier. Booklet 5 is a bit of a mix. It's a calculator paper, but there are quite a few things in there that could come up in non-calculator. Again, we'll talk through some of those. And then this booklet. And the only thing that's not in a booklet is constructions, which we did on a separate little sheet that we did in class. So let's get into the first 2 or 3 of these, starting with indices. Let's write a couple of rules for you. Get my pen ready. Okay. So a couple of things just to mention, particularly some of the harder laws of indices, which are things like this, aren't they? So if I said 16 to the power minus 3 over 2, okay, then to write it in full what that means, minus means reciprocal, so 1 over. The 2 on the bottom of the fraction means square root of 16. However, once I've worked that out, so we'll put that in brackets to mean we work that out first, I then would need to cube that answer. So the square root of 16 is 4, and 4 cubed is 64, okay? Like I said, minus means reciprocal. Just be careful. Reciprocal doesn't necessarily mean 1 over. It generally does, but it can mean to flip a fraction. So if I had something like 1 over 25 to the power minus a half, okay, possibly they'd put that in brackets. Do the reciprocal part first in this case. So flip the fraction, which is 25 over 1, okay, which is 25. And then consider the fraction, which is a half, which means a square root. So I'm actually looking for the square root of that reciprocal. So the square root of 25, which is 5. Okay, so little things like that to be aware of. So we're going to do quite a fair bit of this paper. The square root of 7 times the square root of 7 is 7. And then the third and fourth square root of 7 times it will also give you 7. So 7 times 7 is 49. Anything to the power 0, anything to the power 0 is 1, irrespective of what it is. Now, some people here thinking, oh, the rule here when I times is I add the indices only works really if they are the same thing, okay? So, yeah, if it were 3 squared times 3 squared, you could add the indices, but again, that's not going to help you here because you're looking for the answer, so you wanted to work this out. So 3 squared is 9, and 5 squared is 25. And we're looking to take the square root of that answer, so the square root of 225, which is 15. And here's our first negative indices, so 1 over the reciprocal of 3 to the power 4, which is that one. The only one I'm going to pick up on here, I think, I'll just give you some answers to these without saying too much about them. That was that. Okay. Oh, this is interesting down here, I suppose, because it becomes n to the power 9 divided by n to the power 9, which is 9 take away 9, which is 0. So it gives you 1. Okay. This divide, I would prefer you to think of as over. Okay. 3.4 over 13.6 is actually, well, 3.4 goes into 13.6 4 times. That doesn't mean the answer is 4, it's 1 over 4. Okay, g to the power 6, 8 take away 2 because we're divided. And a different way of writing a quarter of something is to just say it's being divided by 4 there. Again, that's okay, and they all should be alright for you guys, okay? Here is our first dodgy one here. So we've got the square root of 9, which is 3, and 3 cubed, which is 27. Here, that's not so nice. All right, well, let's do the reciprocal first of all, which is 1 over in this case. And then I want the 4th root of 10,000. What times by itself? 4 times to make 10,000, which is 10. Here, let's do the reciprocal first, which is 36 over 1, which is just 36. And then the bottom number means I'm going to be square rooting that. So the answer is 6. Okay, hopefully you can spot here. Okay, again, we want the reciprocal, so 1 over the 5th root and the power 3. There she is. 5th root, power 3, and the minus meaning 1 over. Let's pick one of these at random. I'm not doing all of these for you, okay? So 8, 1, 2 over, that's recurring, so that gets a 9. That's recurring, so that's going to get a 9. And the 8 is not recurring, so it gets a 0, but we have to take away the not recurring bit, and it's better to show that with a line all the way across. So the answer is 804 over 990. Another way that could be asked, I guess, is this. As soon as you spot the recurring decimal, the dot notation, okay, in this paper, that dot notation, as soon as you see it, means make this to a fraction, even if it's involved in another thing like this. We see the dot notation, we turn it to a fraction. So what have we got here? We've got the number after the point of 0, 2, or just 2. But the 0 is important because the 2 is recurring, the 0 is not. We take away the non-recurring bit. So in this case, we're taking away 0. All right, it doesn't make sense to take away 0. It means we're not changing the number, but it's important to keep following the method. So it's 2 over 90. Okay, so what this becomes is a third plus 2 over 90. My pen's a bit slow catching up, but it'll get there, okay? And to add fractions or take away fractions, the bottom numbers need to be the same. So to make that 90, we would times it by 30, and we would do the same to the top. Thirds. Okay. To be fair, the first and last one look fairly similar, okay? The big thing is we can divide thirds. So that's absolutely fine. That would be the square root of 30. I wonder if I can make my pen any thinner. No. Okay, let's try a different colour for this one. Okay, yes, you can divide thirds, right? You can also divide numbers. So if I put 10 there, before that one, and 2 before that, then the 10 would divide by 2 and would give you 5 square roots of 30, for example. Right, so yeah, divide numbers, and the answer is a number. Divide thirds, and the answer is a third. You can also do the same times in. So 3 times 2 of those, times the numbers, because you can times numbers, times the thirds, because you can times thirds. And we also know that the special rule is if the thirds are the same, so the square root of 3 times the square root of 3, for example, the answer would be 3. Am I thinking you'll get a thirds question? Possibly not, because it may be involved in another question, like a Pythag question or something where the answer is a square root, and you're asked to simplify the square root. However, let's have a go at a couple of these just in case what they mean by simplifying thirds is a bigger question, something like this. But my thought process is it probably isn't, okay? So take each term separately. So because these are separated by a plus, we look at the first bit first, then the second bit. So the first bit is the square root of 800 divided by the square root of 2 cubed. And I'm actually going to write that. Now what I want to say to you about this bit first of all is, normally we'd probably go, okay, they make 2, so it would become 2 times that last square root of 2, which kind of works, okay? However, there's nothing to say we can't multiply all 3 numbers together, which might make more sense here to leave the answer as a third. Okay, so we'd get the square root of 800, and 2 times 2 times 2 is 8, but still in the square root. And because they're both now surds, we can divide them. 800 divided by 8, which is 100, and that does have a square root, which is 10. So the first bit, the answer is 10. In the second bit, and I'm only going to do one example of this because we see a lot of this thing, okay, where you've got a bracket with a number and a surd, and we're squaring that bracket, which means we need to write the bracket twice. Get that written down, get that in your brain. A squared bracket means write the bracket twice. We have 4 multiplications to do. That times that, which is 9. That times that, which is 7. But minus times a minus makes a plus. That times that, which we can't do because it's a number multiplying a surd. So the best I could do there is that. Okay? But again, a minus times a plus, so the answer is minus. And finally, that times that, which again is a minus times a plus, so is minus that. Okay, we'll leave that there. We'll just stop the video in a second. So we can simplify this. 9 add 7 is 16, and minus 3 of those. Okay, so if I've got minus 3 of those, and then I take away another 3 of the same thing, we're not multiplying or anything. This is just number line work like we would do in algebra. We get minus 6 of those. Now, we have to add that on to this. We're adding that on to this. You could probably set it out a bit neater than this. So simplified, I can add my numbers, but what I can't do is do anything with those square roots, which remain in the answer. So the answer still contains a surd. Okay, so the answer is irrational. Okay. We'll do this one just because it looks a little bit different. And also, I'm really surprised this came in a non-calculator paper given the size of the numbers, but let's go with it. Pen's not doing brilliantly here, is it? So that's easy enough. 63. That's easy enough. 7, although careful that it's a minus times a minus. And that is not easy at all, because it's the square root of 7 times the square root of 63. Okay, and 7 63s, it's 420, 441, I believe. Okay, which is minus. And then, because it's a plus times a minus, and then this gives you the same answer, a plus times a minus, so it's minus again. 441. Now, I'm dubious that this actually came from a paper 1 because first reflection might suggest you that's a surd, and you'd be well within your right to think, oh, that's a surd, so I've just got minus 2 of them. But actually, this does have a square root. It's not a surd, which you'd know if you had a calculator, okay? The answer to that is actually 21. The square root of 441 is 21. So it's 63 add 7, 70. Take away 21 and take away another one, 21. So taking away 42 from 70. So the answer to that is 28. But I could easily see how you would just write that as that and not realise that it actually wasn't a surd. Okay, not the case though. Okay, the next one, again, expanding a double bracket, giving your answer in that form, which we know really well, another indice. Okay, and we're on to a little bit of simplifying now. Okay, split the number up into a surd times a surd. The most obvious one here is probably 9 times 5. Okay, and the square root of 9 is 3. Always useful for one of your numbers that you're timesing together to have a square root. It'll get you to the answer quicker. So that's that. Okay. All right. We'll try. You can try this one, but I'll try this one. Okay. 8 times 5 is 40. This times this. It's minus, first of all, 3. But the square root of 7 times the square root of 7 is 7. But it's not 37. It's minus 3 times 7, isn't it? Okay. So let me write that again. It's 40 minus, and actually that's 21. Okay, down here we can times the numbers. We've got minus 3 times 5 is 15, but there's no third to times the square root of 7 by, so that stays. And the last one is plus, this is a positive times a positive, 8 square roots of 7. Okay, 40 take away 21 is 19, and minus 15 of these add 8 brings me back up to minus 7 of these. Okay, I think that's okay. I think that would be okay for you as well. As with some of these. Okay, just try them. Right, we'll end with these two. All right, and you fill in the rest and ask me if you've got any problem. Simplify again, split it up. I'm looking at it thinking I could do something like 18 times 4 or something like that, but that doesn't help me very much. But what will help me here is 36 because it has a square root times 2, which is 6 times the square root of 2, which is this one. Okay, and finally, 7 times 3, work it out, work it out, work it out, work it out. And remember, you can times numbers by numbers, you can times thirds by thirds. But a number times a third literally leaves you with a number times a third. So for example, this bottom one here is 7 times the square root of 5. Well, that is 7 square roots of 5. You try and do the rest. And we'll pick back up on the next section. And our next section is quadratic expressions and equations. So the first thing I want to say here, guys, is if ever you're asked to solve a quadratic, okay, if we're in paper 1, that is likely to involve factorising. Okay, it may not say factorise, it may say solve this quadratic and you'll factorise. Okay, if we're asked to solve a quadratic in paper 2, that will be the quadratic formula. And the clue for the quadratic formula is always where they say solve, give your answers, more than one answer, to 2 decimal places or 1 decimal place. There's your hint for the quadratic formula. Be careful that instead of using the word factorise, they say use an algebraic technique. Well, factorising is one of many algebraic techniques. So that you literally look over the clue, ooh, this is a quadratic equation, let's factorise. Okay, so I'll leave you to do 1 and 3 here, and I'll just take the middle one. So let's factorise this first of all. X, okay, and we're looking for 2 numbers. We're looking for team, remember team, times, to make the end number, minus 18, which will add or take away, as it happens, to make the middle number, the number before the x, which is minus 7. And you can have a little look at lots of pairs if you want. You could write every pair and just cross them out, but you'll soon get to the fact that I think 2 times 9 is our way to make minus 7. And to get minus 7, 2 take away 9 will give you minus 7, remembering that the 2 is actually positive. And just a quick check whether that works here. If the 2 is positive and the 9 is negative, then the plus times the minus will give the minus. Now we only really need to look at the signs on this side. And if there's more than one way to make minus 7, which is very unusual. Okay, if there was another pair you thought you could make minus 7, then we'd have to make the signs work for the minus 18. But I'm far more concerned about getting that sign correct. 99.9% of the time, if we get that one correct, the other one will just work. So that's the factorised bit. Now that would be where we'll stop that question there if we get to that stage. But in this question, we have to say no, right. Either x plus 2 equals 0, so x equals minus 2, or x minus 9 equals 0, so x equals 9. Okay, fab. You could try the next one there. So that's a type of factorising, okay, now which you can also try there. I want to pick up something here though, something a little bit new, okay. There are 4 types of factorising. This is type 1, call it. Factorising a quadratic, an easy quadratic, okay. Type 2 would be factorising a harder quadratic, something like this one here. Harder because it's got a number before the x squared. You also have factorising like what we've got in part A here, where it's not a quadratic. It does have an x squared, but the next term isn't an x term, and there's no number term at the end, so it doesn't look like a quadratic. So we look in here, what can I take out of the bracket? This is likely to give me a single bracket. So because I've got a 12 and an 18, the highest common factor of those is 6. That can come out of the bracket. And because there's x's in the first term and an x in the second term, an x can come outside the bracket as well. And I ask myself the question then, 6 times what makes 12? 2, x times what makes x squared? X. Plus 6 times what makes 18? 3. X times what makes xy? Y. Okay? So your three main types of factorising are easy quadratic, hard quadratic, and single bracket. All right? But if you look at part I there and part B there, they don't really fit any of those three categories. Okay? There's no number I can take out for a single bracket. There's no letter I can take out for a single bracket. Yet they don't look like a quadratic. And there's a fourth type of factorising called the difference of two squares. Now I will talk about this in a revision session, probably the half-term revision session, but if you're not there, listening carefully. To factorise with the difference of two squares, and let me tell you, of all the factorising type examples, this is the far least likely to come up. I am mentioning it for you to be aware. You can see it's a little one marker, okay? The rule is, what is being squared there? X. What is being squared there? 10. So x is being squared and 10 is being squared. So this is the difference, the takeaway of two squares. To factorise it, okay, whatever the first thing being squared, which is x, you add the second thing, 10. And then in the second bracket, you put x, but you take away the second thing being squared, okay? And so it's a double bracket factorising. So it's a bit like a quadratic, but it's just got its own little technique. So this one here, think about it. What is being squared here? X. What is being squared to make 16? 4. So my two brackets are x plus 4 and x minus 4. And we'll use that a little bit coming up. The final type of factorising, then I'm going to let you try the rest, okay? Now, be aware of this type of quadratic question. They could ask you this in paper 1 with factorising, or in paper 2 with the quadratic formula, where the first part isn't solve or factorise, it's show that. And there's another one coming up. In other words, prove that that works using the information above. We don't use our method till part B, where we're asked to solve. So, I laid three concrete slabs, okay? 2 of the slabs are square, each side of length x. So I've got a square with length x, and I've got another square with length x. I then have a third slab, which is a rectangle, a width of 1 and a length of x plus 1. And the combined area is 7 meters squared. If I were to write that as a bit of algebra, I would say, okay, the first slab is x times x. The second slab is x times x. The third slab is 1 times that. What if I times in it by 1? You could leave it in the brackets, I suppose, but it's like expanding the brackets, but with a 1 outside, 1 times x and 1 times 1, okay? But we're told that when we add the areas up, we get 7. Now, if we collect these things together, we've got 2x squared, we've got 1x, and if I bring the 7 over to leave 0 there and take it away from the 1, I get minus 6, and I have shown that. But that's not where the marks are here, is it? The marks are factorising to solve and find out what x is, okay? So the difference when there's a number before is we start by doing 2 times the end number. So what we are looking for here is two numbers that times to make the end, but instead of using -6, we times it by 2. So we're looking for two numbers that make -12. But like the other method for easier quadratics, they still have to add to make this middle number here, which is plus. And even though there's not a number written there, that means that that's +1. Okay, my best bet here is 3 times 4. And to make +1, that would be 4 take away 3. The other slight difference with this method, as well as this extra bit here, is that my brackets aren't x plus something or x minus something. They are, in this case, 2x. 2x, because that's there. Okay? +4 minus 3. You then look at your two brackets, and this is the third difference. And if there is a bracket that can be divided by a number, do it. So 2x minus 3 can't. The highest thing I could divide that by is 1, and there's no point. But 2x plus 4 are both in the 2 times table and can be divided. If I half them both, I get x plus 2. And my second bracket is 2x minus 3. Okay? And the solving bit, which is the equals 0 bit, so you can add that on, would suggest that either x equals, and the opposite of +2 is -2, or x equals, and the opposite of -3 is 3, and the opposite of times 2 is divided by 2. Okay? Again, you'll be able to do this one, but just pick, there's not many clues to say what to do is there other than solve. This is a quadratic. It's asking for an algebraic method, and it's not asking for decimal places, so it's not suggesting the quadratic formula. It's suggesting factorising. Here again, you've got a 1 marker, show that. Well, read what's above and see if you can prove it. Doesn't matter if you can't for 1 mark. Then we get to solve. And then if it asks to interpret, a little bit like when we're using the quadratic formula, because we're talking about a distance or a size or a length here or something like that, that one answer will be positive, no doubt, one answer will be negative, and you'll write here, you're going to use the positive answer. Pen is not doing very well anymore, is it? But we'll keep going. Okay, can you continue with that section? Okay, some nasty look ones to end here where you think, oh, single bracket? No, actually not, because there's no number that goes into 4, but also into 169, like 2 doesn't go into 169, like there's 4. Okay, also there's no letter that can come out, so this is one of those difference of two squares. What's being squared here? 2 and an x. What's being squared here? 13. Answer 2x plus 13, 2x minus 13. So one of those difference of two squares ones, as is the last one, but you try that one. Okay, on to algebraic fractions. Something like this one, okay? Right. So what you're going to do here is 4 times this plus 8 times this on the top. Cross multiplying is called. 4 times the bottom of that plus, because that's what in the middle, 8 times the bottom of that fraction. Okay, all over, you times the two bottom things, write them in brackets. So 2x minus 3x plus 6. Lots, right? We've done the first bit, we've done that, we've got the single fraction bit, right? But the simplest form means expand every bracket you see, collect things together, you can collect together, etc., etc., right? So if we do that, but let's look at the method first of all. So it was that times that, then it was that times that, and on the bottom it was that. times that, okay? So on the top, we end up with 4x plus 24 plus 16x, and then 8 times minus 3 minus 24. And on the bottom, we end up with 2x times x, which is 2x squared, minus 3 times x, plus 12x, and minus 18. And now we just collect together things on the top that we can, and collect together things on the bottom we can. So on the top, we can collect our x's together, and we can collect our numbers together, but it's 24 take away 24, which is 0, so they've gone. And on the bottom, well, our x squareds stay alone, because there's no other ones. We can collect our x's together here to make plus 9x, and there's no other number other than minus 18. So that's one type of algebraic fraction, right? Express these two as a single fraction, and that's the method for that. And there's plenty of those to try, okay? Some of them are a little bit harder because you're doing 7x times that, but again, have a go. The other type of question is to simplify, okay? So I've covered the express type question. The simplify question actually relies on factorizing, okay? They could be quadratics, they could be single brackets, they could be difference of two squares like we talked about in the last section. And in this case, the bottom is a single bracket because I can take 2 out of both. The top, there isn't a number that goes into 9 and 25, neither is there a letter I can take out. So this is one of our difference of two squares, okay? And what is being squared? Well, to make 9x squared, what's being squared is 3x. And in the first bracket, we add what's being squared to make 25, which is 5. And in the second bracket, my pen's dreadful, we take it away. Okay, any bracket that we then see on the top that we also see on the bottom can be eliminated. So my final answer here is the bracket 3x minus 5, which is still there, divided by 2. And you don't need to go further than that. You don't need to divide them both by 2. There's just no point. Okay, that's the end of that one. Okay, single fraction in its simplest form. All right, fine. Okay. Solve. We're on to one of these solve ones. Now, what we're going to do here, guys, and this is one we have seen before quite a bit, make the bottom numbers the same. Okay, we're going to make the bottom numbers 12. Times that by 3, times that by 4, times that by 6. But what we do to the bottom, we also do to the top. So the top here needs to times by 3. So it becomes 9x minus 3. Minus, that's what's next. The top here needs to time by 4. 4x plus 24, all of it times by 4, equals the top here needs to times by 6, 18. At that point, because these would all be fractions over 12, we can now not get away with not writing the bottom. So simplify. 5x, 9 take away 4. Then the numbers, plus 21 equals 18. Take the plus 21 over as minus 21. 18 take away 21 is minus 3. And finally, divide by 5. So that's the third kind of algebraic fraction type question, okay? And we go on and we talk about some others. There we are, another simplest form question. Another one making the bottoms the same. Here you can make them 12 again, look. Times that by 4, times the top by 4. Times that by 3, times everything on the top by 3. That one doesn't need to change, so it will stay as 149, and then solve. Okay. It looks weird, but it's the same thing. Yeah, let's get you going. It's 3 times the bottom of the other fraction, plus, because that's within the middle, 1 times the bottom of that fraction. Well, that's just 1 times 4, that's just 4. And then on the bottom, you times those two things together. So this time it's 4 times 2x plus 7. But put that in brackets because, yeah, Just be a bit careful here, I guess. Alright, 6x plus 21 plus 4 divided by 8x plus 28. Okay, and then the only other thing that we can do here, I guess, is we can add those to make plus 25 in our final answer and then leave it at that. Another simplify one, generally suggests factorising, but much, much harder. The top is a hard quadratic. Yeah, so it's going to have a double bracket in it, divided by, I'll leave you with that. The bottom, oh, I think I can take a number out there. It's not a minus, so it's not one of these difference of two squares. I'll take the number 5 out. I'm left with 2x plus 7, and I would love to think one of those top brackets will be 2x plus 7, so that we can eliminate it at the end, but you try it and see. Solve. Okay, dodgy bit here is that this last one isn't a fraction. You need to think of it as 4 over 1. Okay, we need to make them all 10, so we'll times that by 5, times all the top by 5, times that by 2, times all the top by 2. And because that's 4 is the same as 4 over 1, we're timesing that by 10, so times the top by 10, and then solve to find x. Now, this one I'm not going to do on this video. I'm going to do it on Wednesday of half term, and if you're not in, I'll do it with you at another time because it's looks like nothing else and it's very unusual, so I don't want to get bogged down in it. Then we've got another express as a single fraction, and we're on to the next topic. Okay, next section is a little bit to do with angles, so some basic angle stuff, followed by some circle theorems, which is more angle stuff. Then we've got transformations and we're done. Okay, angle facts. It's in the list. There are a variety of them. I would say 90% of them you know. We'll mention parallel lines, something you did with Miss Goose, but we'll mention it, okay? Okay, so here to work out the size of angle x, realise that they add up to 180 and the angle there is 90, so you can work out x. In an isosceles triangle, this is important even for circle theorems, in an isosceles triangle, ladies and gentlemen, 2 sides are equal and 2 angles are equal. So if you have a triangle where 2 sides are equal, then 2 angles are equal, or vice versa. If you're given a triangle with 2 equal angles, then there are 2 sides equal. They still add up to 180, okay? So what I'd be looking to do here, I guess, is take the 34 away from 180, which is 146, and then divide it by 2, because these are equal, meaning that they are 73 each. However, I am asked to find the size of AC, that's the one with the roof, DA to C to D, so actually what I'm doing is here, and because of the straight line here that these two are making when they're put together, they add up to 180, so the angle that I actually need here is 180, take away that 73, which is 107, okay? Here, not a triangle, so the angles don't add up to 180, but in a 4-sided shape, they add up to 360. That should allow you to work that one out initially by adding up the 3 you know and taking the answer away from that to give you that one. Once you know that one, again, you've got those two adding up to 180, so it'll be 180 take away the angle that you've worked out there. One angle in a right angle triangle, well, that's a bit of a confusing thing, isn't it? Because in a right angle triangle, one angle is 90, but what they're saying is one of the other angles is 60. So if it's a right angle triangle, it's got a 90-degree angle, it's got a 60-degree angle, what's the third angle? Okay, leave that with you. And 3 of the angles add in a quadrilateral, well, in a 4-sided shape, the angles add up to 360. 3 of them add up to 250. What is the other one? So what have we got so far? Isosceles triangles, triangles adding up to 180, straight lines adding up to 180, quadrilaterals adding up to 360. Next little rule I guess we've got to know is opposite angles. That's what these are called. And opposite angles are equal, and I'm trying to cut down my writing because my pen not being great here. So angle F is 73, okay? This angle is 180, take away that, because these two add up to 180, so this angle here is 52. We know that that's 73, we know that that's 52, and we know that the three angles inside this triangle add up to 180, so we can use that to work out G. Okay, quadrilateral, fine. Okay, it's using angles, so that's why I've included it, but again, not overly likely, but hey ho. Show that it's not a right angle triangle. Well, the three angles, they are angles, so if they add up to 180, add up what they are. 5x and 3x and 2x is 10x. 1 take away 2 is minus 1, take away 9 is minus 10. But we know that we've added the three angles up, but we know that they are equal to, that they actually add up to 180. And if you solve that, take the minus 10 over and divide by 10, you get x equals 19. Now, if x is 19, two 19s add 1 is 39 degrees. 3 19s minus 2, I think is 55 degrees. Just check that. 3 19s, 19, 38, 57. Yeah. And 5 19s, 50 is 95, take away 9 is 86 degrees. None of those angles are 90, so this, we can state now, we can answer the question and say, yes, this is not a right angle triangle because none of the angles are 90 degrees. Okay, a little bit more tricky, if you read it, the only information, the two bits of information there are already on the diagram. What we are not told, or what is not on the diagram, is that BX is the same length as BC. Oh, in other words, this must be an isosceles triangle. So we've got to prove that AX is the same as BX. So what we actually have to prove is that these two are also the same length. But start here. What they've told us that this is an isosceles triangle. So think to yourself, if this is an isosceles triangle, what size is that? It's 80, okay? Because they've got to be the same. Right, we can go about this a couple of ways now, I suppose, okay? We could work this angle out because we know they add up to 180. I don't know if that one will help me too much. The other angle I can definitely work out is that one because these two add up to 180, so this must be 100. So my reasoning so far, because I haven't written this because it says give reasons, so you'll say angle CXB, that one, equals 80, and your reason you would write because they are equal angles in an isosceles triangle. Then we'll talk about this one, AXB, which is 100, and your reasoning would be because these, the 80 and the 100 need to add up to 180 because they're on a straight line. If that's 100, which it doesn't look like it based on my bad one, and that's 40, they add up to 140, so that must be 40. So you can say that ABX is 40 because angles in a triangle add up to 180. And the final thing to say is, well, if those two angles are both 40, then AXB is an isosceles triangle because it has two equal angles. Therefore, it must have two equal sides, which proves that. Okay, now we're away from our basic rules of isosceles triangles, normal triangles, right angle triangles, quadrilaterals, opposite, all those easy ones, okay? We're on to parallel lines. Now, in parallel lines, the following rules, okay? That angle, that angle, that angle, and that angle are all equal. That angle, that angle, that angle, and that angle are all equal. If I tell you that this one is 100, to keep the number is easy, all the shaded in ones are 100, and what do you think all the not shaded in ones are? Yeah, they're all 80, because each pair adds up to 180, because each pair is on a straight line. Okay, so of the three angles A, B, and C down here, which of those are equal to this? Well, this one would be also this one, also this one, whereas B is the pair, the other one of the pair, so 180 take away 113. Now this is tricky, right? Because what we've got to be a little bit careful of here is what happens if this happens, okay? And I'll draw another version here. That is one line with a group and a group, whereas that is another line with a group and a group. So what you've got up here is a whole mishmash of overlapping groups that are like those two combined up there, which makes this a little bit tough, okay? But what we do know is if that's 52, then that's 52. And if we follow this line up here to the parallel line here, there's where that line is coming through the parallel line. So this is the same, okay? And actually, then A is the same, okay? So A and B are both 52 because they are the same pair as this, right? On here, 116, well, that one should be easy. How are we going to work out 116? This is also 116, but we've got these two then, okay, which will be 64 each. So X is 64. But if you follow the line up, the 64 that is there, if you follow this line up, is also there and would be there, 64 as well, okay? The 116 is a bit easier to spot, because a bit harder to spot, because the 116 is actually running from this line, isn't it, all the way around, and that's not that useful to me there. However, the final angle is nothing to do with either of the lines. It's just being made by the lines. It's where that line meets that line. But you've got yourself a little triangle in there where they add up to 180. Well, you know this one. You know this one. And you can work out what y is there. Okay? And again, this one should be nice and easy for you because this group is the same as this group, and this group is the same as this group. Circle theorems. Okay. This isn't going to be the biggest guide ever. I'm going to refer you on to other things to learn the circle theorems, okay? Yeah, in fact, I'm going to pick a couple of these out and do them as if you know what the circle theorems are, and I'm going to refer you to another video to learn the basics of circle theorems, okay? So go away and watch that other video on Teams first to get your basics, and then come back to this. Okay, let's start with this one then. PQ and PR are tangents to a circle. Okay, our rule of tangents are that this and this, any two tangents from the same point are equal in length. Therefore, by connecting Q to R, like I've done there, that is an isosceles triangle. Okay. The other rule is that if a tangent, where it touches the circle, if you connect that to the center, that angle is 90 degrees, and that angle is 90 degrees. Okay. But that 90-degree angle is made up of that little bit there, which we've kind of put lines through, and this little bit added together, and the same here, it's that little bit and that bit added together makes 90. So it says find the size of O to Q to R. So here, this little bit here. Right. Use the isosceles triangle first of all. If that is 30, take that away from 180 to make 150 and half it. So we've got 75 here and 75 here. Okay, if we know that the angle between a tangent and the centre is 90, and that's the reason, and go to my other video for all these theorems, the angle between a tangent and the centre is 90. If that bigger part of it is 75, then the smaller part of it is 15, and that's your answer for that one. In this one, what do I see? Okay, I see a cyclic quadrilateral. Joining A on the circumference, to B on the circumference, to C on the circumference, to D on the circumference. In a cyclic quadrilateral, these opposite angles add up to 180. Okay, so if you know that one's 71, you can take that away. And if you wanted a reason, you'd say angle D, or even better, ADC. This one here, angle ADC, equals whatever it is, because opposite angles in a cyclic quadrilateral add up to 180. Then to get x, I'm just looking at the little triangle. If I know this one and know this one, I can work that one out. And the reason in there is angles in a triangle add up to 180, but I'll leave you get the answer. Here, the rule I'm looking at here is that arrowhead. Again, if you look at my other video, I'll talk about it. Right, that's a classic look, okay? Where that is at the centre of the circle and that is somewhere on the circumference. So that angle is double that. So it's 148. And the rule is that you'd write, if you have to give a reason, the angle at the centre is double the angle made at the circumference. So the angle made at the centre is double the angle made at the circumference, okay? Now x, okay, dodgy one here. I'm looking at the fact that I've got a little triangle, but I only know one of the angles. However, and also in my circle theorem videos, I'll tell you to keep an eye out for the fact that what this is a little isosceles triangle, because O to A and O to B must be the same size because they're both radiuses of the triangle, okay? So basically, I need to take the 148 away from 180 and then cut it in half to know what x is. And my reasoning there is that AOB is an isosceles triangle, so it has two equal angles. Okay. Right, another classic look, not the arrowhead, but the kind of bow tie look, this look. And in the bow tie look, okay, these two are the same, and these two are the same. All right. So the one that is the same as that is this. I already don't like the look of this one, okay? There's another rule going on here as well, all right? Because one of my lines, which is D to B, is going through the centre. And one of my other circle theorems is if a line goes through the centre and then meets there and there, that is a 90-degree angle. So where that is meeting there, that is a 90-degree angle. Okay, I don't want to go into this too much here, right? But if you need the length of BD now, what you've got, if we just pick out this, not the nicest, is it? You've got yourself a right angle triangle using these two circle theorems, where you know this angle, and I'll write it again because I've gone over it, you know that is 28 because of this circle theorem. You know that is 90 because of this circle theorem. You're told that this side here, C to B, is 4.7, and you're being asked to work out the length BD, which is the hypotenuse of the triangle, knowing the opposite and not knowing the adjacent, and completely ignoring this as if it's not there. Okay? Again, the rule here is that is the same length as that because they're both tangents from the same point, but also where the tangent meets and then joins to the centre, we know that that's a 90-degree angle. So the angle from where the tangent meets the circle joined to the centre is 90 degrees. Question A, what is the length of PA? 12. The reason, like I said, two tangents from the same point are equal in length. And what is the size of PAO? 90, nice and easy. No, the circle theorem we use there is that the angle from where the tangent touches the circle going to the centre is 90 degrees. Okay. Calculate the area of the quadrilateral. Well, it's not a particular shape, is it? But it's made up of two triangles. Okay. So if we just look at this triangle here, which has a base, well, they could be base, couldn't it, of 12 and a height of 4. So you can use base times height divided by 2, and the same here. That's 12, and again, this is another radius, so this must also be 4. So base times height divided by 2, and add them together to get the total area. Delta, okay. You can have a think about this. I can see a cyclic quadrilateral joining A to B to C to D, okay. I can also see this kind of arrowhead shape where that is double that, okay. So let's start by working x out, which is 180. Take away that because they are opposite angles in the cyclic quadrilateral. And once I know x, y is double x because the angle at the centre is double the angle at the circumference. Okay. Now, one we will do in class. These are okay. Let me just end with this one, okay? And again, we'll try some others in class. Okay. The only rule I have, the only circle theorem I haven't mentioned in all these examples is the hardest one, which is called and this one, you don't describe it, it's just got a name. It's called the alternate segment theorem. Yeah, maybe my pen's totally gone. Which is this. If a tangent comes in to a point and then goes back on itself within the triangle, it makes an angle, 74. The ends of that line, where they meet, which is up here, is the same as that. Don't ask why. And the only thing you'd have to say is that ACB is 74 because of the alternate segment theorem. And in the same way, if that's 53, that 53 is being made from C and A coming together at B. Well, the tangent comes in to A there, so that is 53. Okay, you've got two angles here, so you could always work out that third angle by taking those two away from 180. And it turns out that the third angle is also 53 purely by luck. Therefore, two of the angles in that triangle are the same. Therefore, ABC must be an isosceles triangle, which if you read the question, is what you're being asked to prove. And there are a couple of other options up here where we're going to be using that alternate segment theorem, I have no doubt. Like here, for example, if that angle is 2x, if we come back along this line and go to the other angle in the triangle, which is up here, that must also be 2x. But we'll talk about the algebra in this one because it's a little bit nasty. Okay. We'll leave that there. And last up, transformations, okay? It is a higher tier question, we're being told, so it's unlikely to be a translation, a reflection, or a rotation. You try them. I'm not going to go into them. They're there just in case. I am going to jump straight to the higher tier transformation question, which is enlargement. Okay, and I've even put it there on this page. Enlargement, the most likely, especially negative or fraction scale factors. So here, enlarge with a scale factor 2. So basically, we want to draw this shape. What this means is twice as big, 2 times as big. Can't even read that now. Okay, but also twice as far away from C. So to get from C to this corner, I've got 2 squares across and 1 square down. So to get to my new position, I've got to go twice as far, 4 squares away and 2 squares down. I then draw it twice as big, but with a ruler. And that's shape B. Okay. Same thing, scale factor 3, 3 times as big and 3 times as far away, and this time the centre is 1, 2. So to get from there to this corner, it's 1 across and 1 up. 3 times as far away would be 3 across and 3 up, but they then have to draw it 3 times as big. 1, 2, 3, 4, 5, 6. Okay, again, don't think it'll be that. That's too easy. That is not higher tier. These are higher tier. Okay. Scale factor half. Half as big, half as far away. Not twice as big or 3 times as big. Half as big, half as far away. And this time the centre of enlargement is 0, 0, or what we sometimes call the origin. How do I get from there to there? 8 to the left and 2 down. Half as far away would be 4 to the left and 1 down, which is there. But then half as big. So how big is this side? 1, 2, 3, 4, 5, 6. So I'm going to go down 3. And instead of across 4, I'm going to go across 4. That shape there is half as big and half as far away from the centre. And now the proper ones, okay? Looks like a rotation. This is not a rotation because one is bigger than the other. How do I get from A to B? Okay, I don't have a ruler, so I'm going to do this and just hope for the best. However, what you need to do here is connect the same point. So hopefully you can see that that point there is this one here. The long side is there and the long side here is there. So that point is that point there. So if we start connecting these up, but with a ruler, okay, oh dear, you use a ruler, as I said. Then you see that all three meet there. Okay, so what this is an enlargement. Must write it. Enlargement. You write it in full. Okay, the centre of enlargement is where the 3 lines cross. So here it's not 6, 4, it's 4 along the corridor up the stairs. Pen's really going, so I'm glad this video is coming to an end. And finally, the scale factor. Now, whenever it looks like a rotation, it's a negative scale factor because it's being enlarged in the other direction from the dot, not in the same direction. Okay, so it's B is twice as big in the other direction from the dot, twice as big and twice as far away in the other direction from the dot. So my scale factor is -2, and you must give those 3 bits of information at higher tier to get the 3 marks. And the last couple are going to be like that, aren't they? Okay. So if we had to draw it, -2 is twice as big, twice as far away in the other direction. So if we use the origin again, to get from there to there is 1 up, 1 across, 2 up. Twice as far away would be 2 across and 4 up. But because it's minus, I'm going in the other direction. So instead of 1 to the right, it's 2 to the left. Instead of 2 up, it's 4, 1, 2, 3, 4 down. The next point to get there is 3 across and 2 up. The opposite direction and twice as far would be 6 across and 4 down. And the final dot is 3 across and 3 up, which twice as far would be 6 across and 6 down. And as you can see, we end up with what looks like a rotated shape, but actually what it is twice as far away in the other direction. Another one for you to try of those, and another one for you to try there. Again, connect that to that, that to that, and that to that. But this time, ladies and gentlemen, going from A to B, again, it is an enlargement. You've got to say that for a point. You tell me the centre of enlargement by finding it, by connecting the corners, okay? But think about the scale factor. Well, it's going to be minus because the dot is in between them, so B is in a different direction to A, so it's going to be minus. A is twice as big as B, therefore, to go from A to B, B is half the size of A. So the scale factor isn't -2, it's a -1/2. If B were twice as big, it would be -2, but in this case, it's half as big in the other direction. End of video, end of booklet 2. Well done.